Tessa, welcome. It's been great to have you join the team on the project, and the unique things that you bring. What really excites you most about the whole genome programme?
Well, I think I've been incredibly lucky joining this project a little later than when you all started, because actually whole genome sequencing has really come into its own over the last couple of years. Sequencing has become much better, but also actually it is this ability to revisit the genome when new things are actually discovered. I think so many of us have been involved with these panels of genes, and then you suddenly see something else has actually happened and there's nothing you can do. You have to start again. Whereas now we can just ring up our colleagues and say, what about this? Have you seen this report? And I think that is incredibly exciting. Of course, the other thing that is great is the breadth of it. So there are lots of different aspects of it. So you're looking at your carrier testing, you're looking at your cancer genes, you're looking at your cardiac genes, your pharmacogenetic genes. So there is the breadth of the what we can actually do. But to me, it is that insurance policy that we can go back to it as well, which I find very exciting.
So we've loved working with you, and what we found in the cancer world is that up till now we've done a lot of panel testing for single gene alterations, and now we're finding that polygenic risk scores are really, really helpful to stratify populations. How useful do you think they're likely to be in the cardiovascular space?
I think we've always been behind you as far as cardiac genetics. There's always been a couple of steps behind cancer genetics. Cancer genetics, with the discovery of BRCA1 and 2, very early out of the blocks in the genetic field. Cardiac genetics had many, many, many more genes associated with it. But by the fact that there are so many genes just means the polygenic risk score is going to be enormously important. But once again, we're playing second fiddle to you guys, because you're going to be ahead of us. They are starting to look at the polygenic risk scores with the cardiovascular diseases, and I'm not sure if it's the same with the cancer diseases, but they're not the common genes that we've been looking at with the diseases that we associate with a single gene disorder. So I think we're behind, but I think it will be important. But I don't think we're quite there yet. But again, we can go back. We can look at it once we've discovered more.
And say we've got a couple in front of us. This is your area of expertise, and they both had a whole genome done, but they want to do the best that they can to know that they're not going to have a child with a devastating disorder due to the fact that they're both carriers of a recessive disorder. Do you think we're still better off at the moment doing carrier panels for both of them as well?
I think that is the stage. Absolutely, yes.
Right.
And the reason I think you can do the, you can pull out the genes from the whole genome, but the real problem is because you don't have a disease in front of you, you have to know, you have to only look at the mutations that have been described previously. So I think, and there are quirky things, like there are some carriers that are associated with deletions and duplications rather than actually a single mistake. And we'll be there. The whole genome will be able to pick this up, and a lot of the time it is tweaking with the algorithms to be able to undertake this. So I think at the moment we are still limited by known mutations. So for instance, if you are a couple who are a consanguineous couple, so you've married your first cousin, those couples are at a high risk of very rare disorders. And actually at the moment we're really not ready for that, because these are diseases that may not have been described before, or they are diseases where the mutation hasn't prescribed before, something we call private mutations. So I think that is the group that, although they're at high risk, still remain very difficult to investigate. So I think the panels are better because they pick out what we know. And part of the whole genome sequencing exciting is looking for things we don't know. And I think that's a slightly different way of looking at it.
So maybe we'll finish on a bit of a futuristic view, shall we? And do you think eventually the cost of this is going to come down, that we will be able to do everything with one genome, one test? And also, do you think we're going to be able to do it on our desktops?
So when do you think, I'm going to ask you a question, Ross. Do you think we should do this at birth?
So it is very interesting that I went to a workshop once where this was discussed, that at what age should you actually start to obtain this information? And at the moment we do newborn screening, don't we, for some conditions. And so there are some instances where we already do newborn screening for some things that are preventable. The ethical problem is that for conditions that don't occur until later in life, you're effectively taking away somebody's autonomy from knowing about a risk of a condition where they might have made a decision later on not to know. I mean, we all know with cancer predisposition testing, we know from well-published studies that 25% of people take up to 2 years to make a decision to have the test, even after genetic counselling, and that some individuals, they're quite rare, but may even have the test and then suddenly say they do not wish to know the results, and you have to seal the results so that nobody can look at them until they decide they actually want to know. So we would have taken away somebody's autonomy if we'd done that at birth.
But what about, the pharmacogenetics in these children who go deaf if they're given an aminoglycoside, and if they'd had a single gene testing, surely that's good news. You've prevented deafness, isn't it? And you think that would...
And in the cancer field, we know that it is a guideline, it's ethical to test children where you can actually change their management. For example, with now Lee-Fraumeni syndrome with whole body MRI, which is available in certain centres, or for example RET testing, where you actually might remove the thyroid to prevent a devastating thyroid cancer that might shorten a child's life. So that now is considered to be acceptable, where it might change management. So I think this is an area that definitely is for discussion, and it's going to be in the near future.
What do you call the near future?
I think within the next couple of years.
Do you? You think it's
what's your opinion?
I don't know. I think it's going to be difficult, and we see a lot of babies with long QT, for instance. And the question is, when do we test these babies? And at one stage we were taking cord blood. So we weren't even waiting for the baby to be out. We were taking the blood and going off and testing it. And I've slightly rode back from that because I think people should have a baby, not a disease. So it slightly worries me about doing it too early. Now, as far as pharmacogenomics are concerned, I have no compunction that we should be actually doing it as soon as possible. For these diseases, we all know about newborn screening with PKU, phenylketonuria. That has to be a good idea. All these people who have these funny deficiencies associated with which diet can make a big difference from, they must be good to screen for. We now screen for cystic fibrosis. Now, we may not be doing it through genetics, but genetics would be a much better way of actually looking for these diseases. And I think there is so much of our screening, actually we're doing it in a layered way, where genetics would be a much better way of doing it. Ross, as an expert in cancer screening, how do you feel about the liquid biopsies? I'm very excited that people can now have a single blood test and it's going to screen for lots of different cancers.
So I think it's a very exciting technology, And of course, because it's just a blood test, it would be very simple to implement and also implement serially, so you wouldn't just do a one snapshot in time. The problem with it at the moment is that, first of all, you do need a very large tumour load. So in other words, most cases you actually have to have metastatic or spread of disease to actually pick something up in the blood sample. And the other thing is it doesn't work for every tumour type. So for example, for prostate cancer, which is the area that we do research in, it actually doesn't work. We've tried it in very early cases of prostate cancer to see if we can detect circulating tumour DNA, and we can't. What's very interesting is it's possible that you might not need to just look at mutated DNA or changes in the DNA code, but actual methylation of DNA. And that's going to be the basis of a very big trial that's going to occur in the National Health Service shortly in certain tumour types, not prostate cancer because it may not work in that condition, but say cancer of the ovary, colon, and of the breast. And for ovarian cancer, I think that could be potentially very exciting because at the moment, ovarian screening using ultrasound and an annual blood marker, CA125, it may be very good on the day you've had the screen, but it's not been proven to pick up tumours earlier, and you get a lot of interval screening.
Yeah, so I feel that it is going to be a very exciting future for, so DNA is really, and maybe it's going to be RNA. Maybe we're not going to be just looking at the DNA. And if everyone remembers that DNA is transcribed into RNA, which is then translated into a protein in the majority of cases, maybe we will be doing RNA screening rather than DNA screening. So there's huge potential for future research, isn't there, and future...
So to end this futuristic discussion, can I ask you a question? So could you see a time when you might use gene therapy for cardiomyopathies and other cardiac conditions?
Yes, I think gene therapy is being a really difficult issue. And obviously there is a lot of talking about gene editing and removing genes, putting in new genes. And of course gene mutations all work in different ways. So there are those that get a new function, you get gain of function. So, and a lot of you know that very well with your oncogenes, they do something different. And of course, if you've got something like that, your gene therapy is going to be very different than if you've got a loss of function. So I think the difficulty is how much normal gene do you actually need and where can you get that gene into? And of course, with the hematological diseases, you've got a very accessible tissue. So I feel that if you can't treat the hematological diseases, we're going to be really struggling with the heart diseases. But let us take spinal muscular atrophy. That is a devastating disease where these gorgeous children, muscles just simply don't work. They've now got some treatment. There's nianserin where they inject into the spinal cord. There is this new treatment whose name has absolutely left me, where it is a one dose costing £1.3 million at the present time, where that is said is all you will ever know. So they're using RNA interference drugs. So I think for the cardiomyopathies, I think it is still difficult because you've got a very long time the gene needs to be expressed for. And they're certainly struggling with those with the skeletal muscles, such as Duchenne muscular dystrophy, which is a similar sort of disease. So I think it's going to be many years before we truly get gene therapy. I think treatments specific to genes will be much more likely than actually changing the genes themselves.
Tessa, thanks a million.